sense parts. Now we move towards the next, that is B plus tree and B tree. Here we are going to see the definition and how the B plus tree actually appears and also the B tree. And then hashing technique. So now start with the B plus tree. See, B plus tree, these questions are normally many times asking to get question paper on B plus tree. Another thing is that in day-to-day life, B plus T indices or B tree indices are used. Why it is, we will see. Now, B plus T. Okay. Now, what are the disadvantages you think of sequential ordered index? First disadvantage of sequential ordered index is that performance degrades as file grows since many overflow blocks get created after the insertion. Means as we insert a record, if there is a no space in the particular block where it is stored in the overflow block. Okay. And accordingly, we need to update the index. If the new record inserted value is not present in the index, we need to update the index. If we delete the record, we need to delete any tag. In some cases, we need to delete the index records also. Then that's why periodic reorganization entire file is required. As we insert a record, many times these are inserted into overflow block if there is no space in the particular block. And that's why the major disadvantage of index sequential file is that periodic reorganization of entire file. What are the advantage of B plus tree then? This is avoided in B plus tree. Automatically reorganizes itself with small local changes in the case of insertion and deletion. That we were going to see in detail with example. Automatically reorganize itself with small and local changes. Reorganization entire file is not required to maintain the performance. In sequential file, we require to maintain the performance periodic reorganization of file. But in B plus tree, it is not required. Now, the minor disadvantage is there of B plus tree. Extra insertion and deletion overhead, space overhead in the case of index. Advantage is that it is extensively used. I have already told that many times the B plus tree index structure is used for the indexing purpose. Now, the structure of B plus tree. So, listen it carefully, try to understand it. Then we will see how to draw the tree with a simple example. So, a B plus tree, so first we are going to see the properties, then the structure of the node. As it is a tree, node is there, correct? So, a B plus tree. So, in this node normally represent like this. Okay. So, it is represent like this. Whatever. Okay. So, this is the structure of node that we are going to see in detail, and this will be, I don't know what happening here with annotation. It automatically goes. Okay, I will show it instead of this wasting the time. So in this way, it is a structure. So nodes are represent like this, the children of this node, and this is the leaf node. So these are the internal nodes, this is the root node, and these are the leaf nodes. Now what are the properties of these nodes and how to represent these nodes? Now B plus tree, what is the meaning of B? Okay, so all paths from the root of the tree to the leaf of the tree are of the same length. All paths from the root of the tree to the leaf of the tree are of the same length, means it is a balanced tree. It is a balanced tree. You can see here all paths. So if this path we consider 1, 2. If we consider 1, 2. Okay. Means this is only available and this is up to this, it is not allowed. So all paths are balanced. All paths from the root of the tree to the leaf of the tree of the same length. It is at level 3. It is also at level 3. All leaf nodes are at level 3 or level 2 or level 4. So all leaf nodes are at the same level. So path from the root of the tree to the leaf of the tree is equal or same, and that's why it is known as the balanced tree also. Each node that is not a root or a leaf has between n by 2 and n children. So what is this n? That again we are going to see. So each node that is not a root or leaf has between n by 2 and n children. So each node which is not a root and not a leaf means internal nodes, all are n by 2 to n children. Okay. A leaf node, the last node, has between n minus 1 by 2 and n minus 1 values. So values are directly stored there. Leaf node has no next node, correct? So it is the final node, and that's why a leaf node has between n minus 1 by 2 to n and n minus 1 values. If the root node is not a leaf, means if there are children, branches, and level 1, level 2 is there. If the root node is not a leaf node, it has at least 2 children. At least 2. Okay, it depends upon the value of n, but at least 2. And if the root node is a leaf node, means there is a single node. Root node is a leaf node, that there is no other nodes in the tree. It can between 0 to n minus 1 values. And what are these values? That also we will see in the next PPT. So remember these major properties of B plus tree. All props from the root of the tree to the leaf of the tree are same length, balanced tree. Each node that is not root node or leaf node means internal nodes are n by 2 to n children. See, this question normally asks in the objective type question. A leaf node has between n minus 1 by 2 to n minus 1 values. If the root node is a leaf node, it has only at least 2 children. And if the root node is a leaf node, means there is a single node, no other node, it has between 0 to n minus 1 value. Now what is these values and what is that n? First we are going to see the typical structure of a node, B plus tree node structure. P1, K1, P2, K2 up to Pn minus 1, Kn minus 1 and Pn. What is this? Ki, okay, K1 to Kn minus 1. Ki are the search key values. Ki is the search key values. If we consider name of the particular instructor is a search key, then Ki Einstein, then Ilsaid, Kim, John. So Ki are the search key values on which we are going to search the record. It contains up to n minus 1 search key values. A particular node contains up to n minus 1 search key values, that is K1, K2 to Kn minus 1. Now, what is P1 to Pn? It contains up to n number of pointers. Pointers, what is the purpose of pointer? To points to the next node or points to the next file bucket or whatever the records. So it contains up to n pointers, P1, P2 to Pn. So always remember the pointer numbers are greater than the search key value, 1 greater than the search key value. There are n minus 1 search key value where there are n number of pointers. Now, what is this P1, P2 to Pn? Pi are the pointers, points to the children, okay, for non-leaf nodes. Pi are the pointers that points to the children, means if it is a non-leaf node, then it points to the children. Okay, whatever the next. It points to the children, whatever the next. It points to the children in this way. So, Pi, if it is not a leaf node, then it points to the children. But if it is a leaf node, then it pointers to a records or buckets of records with that search key. Means here it directly points to the record with that search key value. Means if Einstein, it points to the record with Einstein if it is a leaf node. If it is a non-leaf node, it points to the children. Now how it points, what are the values, that also we are going to see. Now the search keys are in node are always ordered. The search keys in a node are always ordered. K1 is less than K2 is less than Kn. Means if it is a number, it is a numerical sequential order, and if it is a alphabetic, then it is an alphabetic order. Means if we consider our search key is a name, then Einstein always come first, then Ilse, whatever the names, then Mozart. Okay. Then U, etc. So, have you understood? All the search keys are in the sequential order or in some increasing order. If it is a alphabetic order. If it is a number, then in numerical order in a particular node. So that is about the node structure of B plus tree. It is common for leaf node and non-leaf node. It is common for leaf node and non-leaf node. Only the difference that the pointer pi in non-leaf node points to the children, while pointer pi in leaf node points to the actual record with that particular search key. The search keys in any node are always in order. Now see first leaf node. Now properties of a leaf node. As I told that there are 1 to n minus 1 search key values in a node and n number of pointers. Now, for I is equal to 1 to n minus 1, for I is equal to 1 to n minus 1, pointer pi points to a file record with the search key value ki. Pointer pi, suppose this is a pointer pi, we call it as a, suppose I write here, it is in our case. It is suppose P1 pointer, sorry, it is K1, not it is a search key. It is pointer P1. Then this is search key K1. This is pointer P2. This is search key K2. This is pointer P3. This is search key K3 and this is pointer P4. So what is the value of n here? Anyone? Write it in chat box. What is the value of n here? So n value of n is equal to 4 here. Why? Because there are n number of pointers. P1, P2, P3 and P4. So we can say here n is equal to 4. N is equal to 4 and therefore there are 4 pointers in this example. Along with there are 3 search keys K1, K2 and K3. Now what is the property of leaf node? For I is equal to 1 to n minus 1, pointer pi points to a file record with the search key value ki. Means this pointer P1 points to the record with the search key value K1. So Brandon is the search key. So this pointer, look at here where it points. It points to the record with Brandon. You can observe it here. Yes, it is point to the record with Brandon. It is leaf node. Calipari. So it points to the, this pointer points to the record with the ki. That is Calipari. Search key. Creek. This pointer points to the record with creek. And now what about this pointer? What about this pointer? It points to the next leaf node. Sorry. It points to the next leaf node. If it is there another leaf node, then it points to the next leaf node as it is shown here. So the last pointer points to the next leaf node. Last pointer points to the next leaf node. Now, if there are multiple leaf nodes, Li and Lg are the 2 leaf nodes, I is less than j, then all the search key values in Li are less than or equal to all the search key values in Lg. So you can see here, all these search key values are less than this one. All these search key values are less than this one. All these search key values are less than, all these search key values are less than this one. All these search key values are less than this one. Means all these search key values in the leaf nodes are in increasing order. B to W. All search key values in the leaf node are in increasing order. If it is alphabetically or if it is a number. So, all the search key values in the previous leaf node are always less than all the search key values in the next. And the last pointer points to the next leaf node in the search key order. Now, One property of the leaf node in B plus tree is that the B plus tree index is used as a dense index. Dense means every search key value must appear in some of the leaf nodes. Every search key value must appear in some of the leaf nodes. So the B plus tree index is used as a dense index, that every search key value must appear in the leaf node. Means if there are these search key value as the name as a search key, then each and every search key appear in one of the leaf node according to their alphabet. In non-leaf node, for non-leaf node, it is structure is same. There are n number of pointers and n minus 1 number of keys are there in the non-leaf nodes. Non-leaf nodes are also known as internal nodes. There is a difference in that only that in the leaf node is a dense index, while non-leaf node is work as a sparse index. Means some of the search keys appear in the non-leaf node. Now the pointer, what is this pointer P1, P2 to Pn represent? The pointer Pi, the pointer first pointer P1 points to the subtree that contains the search key values which are less than K1. Which are less than K1. The pointer P1, see again I am repeating, the pointer P1 points to the subtree that contains those search keys which are less than K1. Means suppose it is a Mozart, then the pointer P1 points to the subtree that contains all the search key values which are less than M. Alphabetically which are less than M if it is a Mozart. Then what is pointer P2 to remaining n minus 1? So the pointer P2 is points to the subtree whose search key values are greater than or equal to K1 and less than K2. Greater than or equal to K1 and less than K2. Means if it is a Mozart, then pointer P2 points to the subtree whose values are greater than or equal to M. Means Mozart is also there and less than K2. So in general, pointer Pi points to the subtree that contains those search key values which are less than Ki and greater than or equal to Ki minus 1. Pointer Pi points to the subtree that contains those search key values which is less than Ki and greater than or equal to Ki minus 1. And the last pointer Pn points to the subtree that contains those search key values which is greater than Kn minus 1, equal to greater than or equal to Kn minus 1. The pointer Pn points to the subtree that contains those search key values which are greater than or equal to Kn minus 1. Again I am repeating, pointer P1 points to the subtree that contains the search key values which are less than K1. Means if it is a Mozart, less than M, Mozart, whatever are here. And the pointer P2 points to the subtree that contains the search key value greater than or equal to K1 and less than K2. Means pointer Pi points to the subtree that contains the search key values which are greater than or equal to Ki minus 1 and less than Ki. And the last pointer Pn points to the subtree that contains those search key values which are greater than or equal to Kn minus 1. Which are greater than or equal to Kn minus 1. That is about the non-leaf node. See this example and we try to draw one or two B plus tree. Now see the drawing of B plus tree. When we start to draw the B plus tree, the first thing that is which one we have to use, for example search key we have to use as a root node. That is one of the question. Now see, actual when we start the implementation of B plus C, when we perform the program, we need a simple algorithm. So in which random algorithm is normally used to find out the root of the tree. And accordingly the algorithm is implemented. There are so many algorithms available for the implementation of B plus tree. That part we are not going to see. Programming part, only we are going to see how to draw the B plus tree considering any one of the root nodes. So randomly we are going to choose any one of these keys as a leaf node. So here the name is used as a search key. So all these names are written here in ascending order. Correct? Search key values are in sequential order. So I am going to draw it here for you on it. Now we start with randomly. For example, suppose start with Mozart as a leaf node. See, again I am sorry, not a root node. Again I am repeating that any one of these can be used as a root node. It consider the algorithm is there. Now suppose we consider Mozart as a leaf node with n is equal to 4. So n is equal to 4 means there are 4 pointers. So how many search keys we can use there? There are pointers. How many search keys? Fast. No one is writing here answer in chat box. I am expecting your answer. If n is equal to 4, how many search keys are there? N minus 1. Correct? So in a node, we can write maximum 3 search keys. So we start with the Mozart. Now we go for the subtree. Now see this subtree and all these keys, it should follow the rules of leaf node and long leaf node, the pointers P1 to Pn, okay, whatever. Now this is our pointer P1, correct? This is K1, this is P2, this is K2, this is P3, K3 and P4. So this subtree, okay, this pointer points to the subtree whose values are less than Mozart, correct? And this pointer, this one points to the subtree whose values are greater than Mozart. So here we are going to draw here a subtree. Again the non-leaf node structure is same. Here suppose, see here Mozart where it is Mozart is here. So many values are there before Mozart and there are 3 values after, correct? Among these, suppose randomly I choose Einstein and gold. I choose Einstein and gold in this subtree. Not necessary that you have to use all the pointers and all the search key values. It whatever the required, that only we use. Suppose I use here. See, again the pointer P1, the pointer P1 points to the subtree whose values are less than P1. Okay. So I use here Einstein and gold. Remaining there are 3 values. So here in this I use Srinivasan. I use Srinivasan. Okay. Here in this it is becomes P1. This is K1, P2, K2, P3, K3 and P4. In this it is P1, K1, P2, K4. Now how many are there before? There are 3, correct? Before Einstein and gold, now here only 2 are remaining. So now we can move towards the, use it as a leaf node. So this pointer P1 points to the search key values which are less than Einstein. So Einstein, less than Einstein, how many are there? Less than Einstein, there are 3, Brandon, Calipari and Crick. So here I use a leaf node with values Brandon, then Calipari and Crick. So all the pointers and search keys are used here. It is P1, K1, P2, K2, P3, K3 and P4. Okay. Now this pointer points to the subtree which is greater than or equal to Einstein and less than or equal to gold. Correct? this pointer points to the subtree whose search key values are greater than or equal to Einstein and less than gold. So in this example, greater than equal to Einstein means first we need to write the Einstein. As it is a leaf node, means every search key should be there. So Einstein. Less than gold, there is one, that is ill size. Less than gold, there is one, that is ill size. Now after this gold, okay, this pointer points to the subtree whose search key values are greater than or equal to gold. Greater than or equal to gold, and here it is Mozart, means less than Mozart. So it includes gold, cards and Kim. It includes gold, cards and Kim. See once again. Now this non-leaf node points. This leaf node points to the next. This leaf node points to the next. This one next. See once again. We use Mozart as a root node. Then Mozart. Suppose this pointer points to the record with the search key less than Mozart, and this pointer points to the search key greater than or equal to Mozart. So before Mozart, there are so many values. Among that two we have used, that is Einstein and gold. Einstein and gold. Here we use Einstein and gold. So now, and here it is greater than Mozart. So there are three values greater than Mozart. Among the between values Srinivasan we have used here. Now we start with this non-leaf node. Now we are start with this non-leaf node. So this pointer P1 points to the record which are less than Einstein. So less than Einstein, there are three records which are less than Einstein. That is, sorry, it's very sensitive board. Okay. So less than Einstein, there are three records. Okay. So these three records are this Einstein, Brandon, Calipari and Crick. Now this pointer P2 points to the records which are greater than or equal to Einstein and less than gold. Okay, less than gold and greater than or equal to Einstein. So greater than or equal to Einstein and less than gold, there is a single record in. So that comes here with Einstein and ill size. So equal to. After that, gold, there is a pointer P3 which points to the record which are greater than or equal to gold and less than this one, correct? Mozart, less than Mozart. So here greater than gold and less than Mozart. Which are these? Greater than or equal to gold, gold, cards and Kim. So we use here gold, cards and Kim. Now this one. So this pointer P1 points to the record which are less than Srinivasan. So I'll write it here. Less than Srinivasan. So less than Srinivasan and greater than or equal to Mozart. Correct? Greater than or equal to Mozart. So there is Mozart and Singh. Less than Srinivasan, there are two records, that is Mozart and Singh. See once again. Now this pointer P1, this points to the record which are less than Srinivasan, and here it is related to Mozart, means here Mozart we need to add greater than equal to Mozart. So it comes Mozart and Singh. And this pointer points to the record which are greater than Srinivasan or equal to Srinivasan. So there are two records which are equal to and greater than Srinivasan and U. Srinivasan and U. Okay. So you can observe here this pointer points here and this pointer points here. All leaf nodes are in sequence. Now this pointer, what it points? It points to the actual record in the file with Brandon. It is actually points to the record with Brandon. This pointer points to the record with Calipari. This pointer points to the record with actual record in the file. Now, if you observe all leaf nodes, these are all in ascending order of their alphabetical order of their search key values, Brandon, Calipari, Crick, Einstein, Ilse, and you can observe that all search key values are appear in in leaf nodes, some of the leaf nodes. Is it clear to everyone? Again, I am going to show you one more example. See, again I am repeating, it depends upon the person who are drawing this D plus tree. Every person can write it in different way. It is possible. Means I use here Einstein and Gold. Instead of someone may use here Crick. Someone may use here Calipari. It is possible, and their simple algorithms are used to implement the B plus tree, which use the random function to suggest the search key values or to select the search key values. Only rule is that search key whatever we are going to insert for this pointer less than Mozart. Whatever the search key is insert for this pointer greater than or equal to Mozart. Whatever the search than Einstein, whatever the search keys point greater than or equal to Einstein, less than Gold. Is it clear? See, one more example I am going to show you here. I am going to use here the different search key as a leaf node. Here again I am saying n is equal to 4. And I use here ilset as a root node. Okay, search key in the root node. Now the subtree. The subtree points, this pointer P1 points to the, this is K1, this is P2. So pointer P1 points to the record which are less than ill side. So less than ill side, there are 1, 2, 3, 4. Okay, which are, there are 4, 1, 2, 3, 4. You can see Einstein, Crick, Calipari and Brandon. So I use here Calipari. After this pointer P2 points to the record which are greater than or equal to ill side. So after ill side there is Gold, Card, Kim, Mozart, Singh, Srinivasan and U. Suppose I use here Kim and Singh. Kim and Singh. Suppose I use Kim and Singh. Now we move towards the leaf node. Now Calipari, there is a single value before Calipari, that is Brandon. So this pointer points to the record or the search key which are less than Calipari, that is Brandon. Okay. There is a single search key which is less than Calipari, that is Brandon. Now this pointer points to the subtree which is greater than or equal to Calipari. Greater than or equal to Calipari. As it is a leaf node, first we write it as a Calipari. Then greater than or equal to Calipari and less than ill side. So greater than or equal to Calipari, greater than Calipari and less than ill side, correct? Less than ill side, there are Crick, Einstein and Crick and Einstein. So is it fit here? Yes. Crick and Einstein. Okay. So observe here, this pointer P1 points to the record which are less than Calipari, that is Brandon, and this pointer P2 points to the record which are greater than or equal to Calipari. So Calipari, Crick and Einstein which are less than ill side. Now we move towards the next one, this. So it pointer points to the record which are less than Kim and greater than or equal to ill side. Ill side we need to add. It is less than Kim and greater than ill side. So ill side comes there first. Then less than Kim, there is a Gold and Cards. Okay. Ill side, Gold and Cards are less than Kim. So here I write Gold and Cards. Now this pointer, this is P1, pointer P2, this points to the record which are greater than or equal to Kim and less than Singh. So greater than or equal to Kim, it is Kim itself and Mozart, which is greater than or equal to Kim and less than Singh. So Kim and Singh. Okay. So this pointer points to the record, this one P2 points to the record which are greater than or equal to Kim and less than Singh. Sorry, less than Singh, not it is a Mozart, it is Mozart, not Singh itself. Okay, so less than Singh, there are two records, Kim and Mozart. So Kim and Mozart. Now this pointer P3, this pointer P3 points to the record which are greater than or equal to Singh, which are greater than or equal to Singh. There are three records. Can it fit in one? Yes, we can maximum three records in one. And two. Okay, is it clear? Is it clear to everyone? Yes or no? Am I audible? Okay. So this is another example with n is equal to 4. Again, I am repeating. I use here Ilsaid as a root node. Anyone randomly less than Ilsaid. Here this pointer P2 points greater than or equal to Ilsaid. I use here Calipari randomly. Kim and Singh I use here. Then this pointer P1 points to the record which are less than Calipari. P2 points to the record which is greater than equal to Calipari, less than Ilsaid. Then this pointer points to the record which is less than Kim, greater than this Einstein. There are three records. Then this pointer points to the record which are greater than or equal to Kim, less than Singh. There are two records. This pointer points to the record which are greater than or equal to Singh. There are three records. And these leaf nodes, this pointer Pn points to the next record with that search key order. So now I think it is clear to everyone. See, there are different ways, and again I am explaining algorithms are there which are used to draw this B plus tree. Different algorithms are used to draw the B plus tree. Another example I will show it here with PPT. So that is the example. First we have seen root node Mozart, internal node sleep node. Now this Brandon, it is you point to the record with Brandon. This pointer points to the record with Calipari. This one points to the record with Creek in this way. Now another example. Here we seen the two examples with n is equal to 4. Now if n is equal to 6 or n is equal to 5, n is equal to 6 means how many number of pointers are there? N is equal to 6. No, 5, not 5 further. If n is equal to 6 pointers are there. How many number of pointers are there? 6 pointers are there. Okay. And how many number of search keys? 5 search keys are there. How many number of search keys? 5 search keys are there. N number of pointer and 5 search keys. So another example is shown here. Ilsaid and Mozart, two are taken as a search keys in the root node. So this is root node. Okay. And as there are n is equal to 6, only 2 levels are there. At the second level, no internal nodes are there. At the second level, only we can show it as a leaf node. Now see the records, the leaf node, the search key records are here less than okay. So this pointer P1 points to the records with are less than Ilsaid. So less than Ilsaid there are Brandon, Calipari, Creek and Einstein. 4 records are there. As n is equal to 6, 5 search keys we can enter. So all these 4 search keys are entered here. Now this pointer P2 points to the record which are greater than or equal to, it says less than Mozart. So there are 4 records which are greater than or equal to il says gold, cards and kib, which is less than Mozart. And this pointer P3 points to the record with the search key values greater than or equal to Mozart. So Mozart sings Srinivasan, and so here there is a single label B plus 3. At the second level only the leaf node appears. Is it clear? Now see the B plus 3 file organization. This is about the indexing, correct? All these about the indexing. This is the index which contains the search key and a pointer, and that pointer points to the record. Now see, suppose I want to search a particular record with the particular search key. Then how this works? How this B plus 3 works? Here suppose I want to find the record with search key crick. I want to find the record with the search key crick. So start from the root node. Now see here in the root node. Okay. So start from the root node. We are going to find out the record with crick. Okay. We are going to find out the record with crick. So start with the root node. Whether crick is less than or greater than Mozart or equal to Mozart, it is less than Mozart. C is alphabetically less than M. So here follow the left pointer. Okay. Because if this pointer P1 points to the record which are less than Mozart. Now here we comes to the non-leaf node or internal node. Now here find out the search key which is greater than or equal to this crick. What is that? It is Einstein. Nearby crick, it is Einstein. So follow the pointer. It points to the record here. Okay. Crick is less than Einstein. So follow this pointer. Now it is a leaf node. Now sequentially search whether it is a crick. No. It is not a crick. Whether it is a crick? No, it is not there. Here we got a crick. Follow this pointer. This pointer points to the record with the search key crick. Have you understood how to locate a record with the B plus 3 index? Another example, suppose I want to find a record with Srinivasan. Okay. I want to find a record with Srinivasan. So start with the root node. Then follow the pointer. So now what is Srinivasan? It is greater than Mozart, and that's why follow this pointer P2. We need to follow the pointer P2, and then it points here. Now Srinivasan, it is equal to Srinivasan, correct? Srinivasan equal to Srinivasan. So whether this pointer points to or whether this one. This pointer points to the record which is equal to or greater than Srinivasan. So equal to greater than means follow this pointer. The first record is with the Srinivasan. This pointer P1 points to the record with the search key value Srinivasan. Here we will get the Srinivasan record. Is it clear to everyone how to locate a record with the B plus 3? And if the size of tree is less, if n is equal to big, then the number of levels are less. So in that case, minimum number of or minimum time is required to locate a particular record. Now B plus 3, why it is useful? Here in data simple sequential file organization, what happens as the grows the file or increase the size of the file, what happens many times we need to reorganize the file because the new records are inserted in the overflow node, and that is not required here in this. Leaf nodes in this are always what we say contains all the record. It is a dense index, and non-leaf nodes are sparse index. You can see here in the non-leaf node all records are not available. Some of the record are there, but in leaf node there are all records. So leaf node is just dense index, while non-leaf nodes follows the sparse index. Now B plus tree file organization. So in B plus tree file organization, the nodes itself consist of the records. Leaf node consists of the records. Here see the records are separate. Here the pointer is there which points to that particular record from the leaf node. In B plus tree file organization, the leaf node contains the record itself. It is shown here with simple example, not a big example given here. Okay. So here it shows the record A4, B8. The record is directly there instead of pointer. You can observe here pointer is not used. The remaining structure is same. This one points to the record search key which are less than I. This is point to the record which are greater than or equal to I. Then this one points to the record which are less than C. So A, B. This one points to the record which is greater than or equal to C and less than F. So C, D, E. This one points to the record which are greater than or equal to F, less than I. That's why it is F, G, H. Then this one points to the record which are less than K, less than K and greater than this I, equal to I. So I, J. This one points to the record which are equal to or greater than K, less than M, K, M, same. Only the difference is that here the leaf node contains the record itself. Okay. So good space utilization is here instead of using the separate file. Here the separate file is used. Instead of that, here the records are stored in the leaf node. But it is useful when the size of record is minimum or limited. If there are size of the record is very big, then it is not useful to store the records in the leaf node itself. Instead of that, the simple method this is used to store the records in separate blocks. Now we move towards the next, that is B tree index file. Similar to B plus tree, okay, B tree has leaf nodes and non-leaf nodes. Leaf nodes and leaf nodes. But here major difference is that allows the search key values to appear only once. Eliminate the redundant storage of search key. Here you can observe that there is a redundant storage of search key. B plus tree. Mozart appears here. It is appears here also. Correct? Mozart appears here. It is also appears here. Srinivasan appears here. It appears here. Einstein appears here. Appears here. Gold appears here. Appears. So there are if hundreds of search key values, then the search key value may appear many times. It may appear in the root node, non-leaf nodes, and also in the leaf node. So B plus tree use the redundant storage of search key, while B tree allows the search key value appear only once. Eliminate the redundant storage of search key. Search keys in non-leaf nodes appear, means if the search key is in non-leaf node, it appears nowhere in the B tree. But there we need additional pointer, that is bucket pointer. Here we need additional pointer, that is bucket pointer. Now see the structure of leaf node and non-leaf node. Now the leaf node structure is same as we use in B plus tree. There are n number of pointers. Okay, there are n number of pointers and n minus 1 number of search key values. So P1, P2 to Pn, these are number of pointers. K1, K2 to Kn minus, these are search keys. The pointer P1, this is the structure of leaf node. This is the structure of leaf node. So the pointer points, P1 points to the record which is equal to K1. P2 points to the record which is equal to K2. Pn points to the record which is equal to this one and in this way. Now there is a difference in non-leaf node. Leaf node is same. No difference in the leaf node as it is, as we have seen in the B plus tree. Leaf node is same. The pointer, this pointer points to the record with Brandon, this pointer points to the record with Calipari, this one points to the record with Crick. So same structure is here. Now the non-leaf node, there is another pointer is used, that is pointer bucket pointer or B1 pointer. Now for which purpose this is used? For which purpose this is used? This is used for the purpose that here this one bucket pointer points to the record which are equal to K1 and this pointer points to the record which are less than this K1. This one points to the record which are less than K2, greater than K1. Now see it with example, then it becomes simple to understand. The same B plus tree we have drawn here, the same is drawn here. Here, the Mozart appears 2 times, Srinivasan appears 2 times, Einstein Gold appears 2 times, but it is not here. Now, in the root node, we use here 3 search key values. N is equal to 3. As it is not a leaf node, bucket pointer is used there. Bucket pointer is used here. So, here P1 to Pm number of, there are P1 to Pm number of pointers. K1 to Km minus 1 number of search keys and B1 to Bm minus 1 number of bucket pointers, where M is always less than N. M is always less than, why? The size, it requires more space for bucket pointers, and that why the number of pointers stored here are always less than leaf node. Is always less than leaf node. If there are n number of pointers in the leaf node, there are m number of pointers in the non-leaf node, where m is always less than n. Why? Here it requires extra space for this bucket pointer. It requires extra space for this bucket pointer. Okay. Now see here. So that is shown here. Einstein, cards and Singh. You can observe that along with that there is a bucket pointer. So pointer P1 points to the record which are less than Einstein. Pointer P1 points to the record which are less than Einstein. You can observe here which are less than Einstein, and pointer B1, the pointer B1 points to the record with Einstein. It is not shown here, the record means the file, but it points to the record with the Einstein. So we call it as a bucket pointer, which points to the record with equal to Einstein. Pointer P2 points to the record which are less than cards, and B2 points to the record equal to cards. This one points to the record which are less than Singh, this one equal to the greater than Singh. So this pointer comes here less than Einstein, Brand, Calipari and Crick. There are 3 records which are less than Einstein. In this pointer points to the record with Brandon, this pointer points to the record with Calipari, this pointer points to the record with Crick. Now this pointer points to the record which are greater than Einstein, less than cards. So this pointer points to the record which are less than Einstein, greater than cards. So greater than Einstein, less than cards. So you will say and whole. This pointer greater than cards, less than Singh. So Kim and Mozart. And this pointer points to the record which are greater than Singh. So Srinivasan and Wu. So what you observe here? The search key value appears only once. Search key value appears only once. So now you can tell me or how to locate a record in B3. Suppose I want to locate a record with gold, with the search key gold. How to locate a record? So here check the search key value which is less than gold. Search key value which is less than gold. So where it is? It is which is less than gold. Follow the pointer here. Whether it is gold? No. Yes, it is gold. Follow the pointer. Here we will get the record. Suppose I want to record with Srinivasan. So find out the search key which is less than Srinivasan. Which is less than Srinivasan? Think. Follow the pointer. This pointer. The first record is Srinivasan. Follow this pointer. Here you will get the record of Srinivasan. So that is the way we locate the record. Now, what are the advantage and disadvantage of B tree and B plus tree? Write it in chat box. Fast. So advantage of B plus tree is that here the in non-leaf node also we can store more number of search key values. But here in non-leaf node the search key value storage is less. Another thing is that in B tree there is no redundancy, but in B plus tree there is a redundancy. That is the difference, major difference, that in B tree there is no redundancy of search key, while in B plus tree there is a redundancy of search key. Now see the difference. Advantages of B tree indices: may use less tree nodes than a corresponding B plus tree. You can see here the number of tree nodes 1, 2, 3, 4, 5, 6, 7, 8 in B plus tree, while in this there are only 5 nodes. So the number of nodes in B tree is less than B plus tree. Sometimes possible to find the search key value before reaching the leaf node. In B plus tree, every time we need to reach the leaf node, then only it assigned to the record or point to the record. But in B tree, it may be possible that records are appear before the leaf node. Here, if you want to find a record with card, easily you can find it here. Not necessary to reach to the leaf node. That is another advantage of B tree. Avoid redundant storage of search key, that already I have told you. But it has some disadvantage. Only small fraction of search key values find earlier. Insertion and deletion is complicated in B tree, and also the implementation is complicated in B tree. Insertion and deletion is simple in B plus tree. Implementation is simple in B plus tree. So that is about the B tree and B plus.
Now we move towards the next topic, that is multiple key access. So multiple key access, there are two concepts in multiple key access. The first one is that use multiple indices. Use multiple indices means we consider for instructor relation there are two indices. One is on the department name, okay, one index on the department name, another index on the salary. That is the first concept, that use multiple indices, two indices, three indices, etc. Or another approach is to build a multi-attribute index. Okay, multi-attribute index means we build a single index with two attributes, department name and salary. Okay, so these are the two approaches in multiple key access. So first approach we are going to study. We consider two indices here, multiple indices. We can consider two indices, department name and salary. Suppose there are two indices, one index on the department name and there is another index on the salary. So we execute suppose a query, select ID, we want the ID of the instructor or the instructor relation where department name is equal to finance and salary is equal to 80,000. Then when we execute this query and if there are two indices, one on department name and another on salary, then how it executes? How it executes? So there are three possible strategies for the execution of processing of this query using two indices. Okay. The first strategy is that we start with use the index on the department name and find out the tuples with the department name is equal to finance. Okay. So use index on the department name to find the instructor with department name finance. And then suppose we got 10 tuples with the department name is equal to finance. Then from that select the salary is equal to 80,000. Find out only those tuples whose salary is equal to 80,000. That is the first strategy. The second strategy is that use the index on the salary and all the tuples with the salary is equal to 80,000. Suppose there are 5 tuples with salary is equal to 80,000 and from that 5 tuples one by one sequentially select department name is equal to finance. So these two strategies are used. Third strategy is that the pointer method is used. So first we use department name index so to find the pointers to all tuples with the department name is equal to finance. Means suppose I write here department name and salary only I write here. Suppose finance department salary 20,000, then finance salary 80,000. Then music, this the salary 80,000. Then with salary 80,000. Then computer science with salary 80,000. Okay. Suppose these are some records are there. So the last approach is that which are pertaining to finance department. So now check which are the finance department. So here we say one pointer, first, second, and third, 3 pointers. Now similarly use the index on salary and find out the tuples with the 80,000 or pointers to with the 80,000. So this first 80,000, 80,000, 80,000, and 80,000. Okay. Now these 4 pointers which point to the records with the 80,000. Now make the intersection of these two. So when we make the intersection of those two, we will get this tuple with the finance and 80,000, and we will get this tuple with finance and 80,000. So that simple strategy is useful. So it is useful. This kind of two indices or multiple indices are useful if there are multiple tuples with these values. Now see another example or another method, indices on multiple keys. So composite search keys are some used here contain one or more attributes. So we consider there is an index on the department name and salary together as a single index. Now say when we consider a single index with multiple attributes, we need to follow the lexicographic ordering that A1, B1, A1, A2 is less than B1, B2. So A1 always less than B1 in lexicographic order when we consider the indexing. If it is equal to B1, if it is same, then A2 must be less than B2. Now see with example. Suppose we have, first we consider A1 and the CSE, comma, 30,000, salary, okay, is always less than, I write here, music with 30,000. Correct? Here, A1 is less than B1. CSE, C is alphabetically less than M. So that is, if it is not there, if A1 is equal to B1, means CSE, comma, 30,000 is less than CSE, comma. So here A1 is equal to B1, both are CSE. So in that case, A2 must be less than B2. Then we call this set is less than this set. Everyone clear? So it should follow the lexicographic order when we consider multiple search keys in a single index. Now see example, the same example, suppose we want to find the ID of the instructor with department name is equal to finance and salary. So here two indices, two search keys are there. So here we got the result is equal to the tuples with the finance, tuples with the is equal to salary. Both conditions are satisfied, then we give the result. It is also useful when department name is equal to finance and salary is less than 80,000. Okay. Why? Because there are so many departments of records with the finance and salary is less than 80,000. But if we write a query, department is less than finance and it's the salary. Salary is equal to 80,000. So in that case, it is not useful or not efficient to handle such kind of query because there are so many records which are less than finance. In biology, biotechnology, or your all whatever CSE, electronics, all comes before the finance. So there are so many records less than finance, but very less records with salary is equal to 80,000. And that's why it is not efficiently handled with this kind of query. But for these two kind of queries, it is useful to use two search keys in a single index. That is the simple concept of multiple indices or multiple key access. So these kind of questions normally asked for the write short note on for 4 to 6 months. Now the index definition in SQL that we are going to execute for practical, we are going to create the index, actual index for your table that already you have created, for the relation that you already you have implemented. So here, create index, simple syntax is that create index in bracket index name on relation name attribute list on which we are going to create the index. So example is given here, create index. So create index, it is a keyword. Then in department index, it is the name. It is the name given to that index. You can give any name, department index. On again keyword. On which relation we are going to create the index? On the instructor. And which attribute we are going to use for index? That is department name. So when we execute this query, create the index with the name department index on the instructor with attribute list department name. So attribute list means one or more attributes are also. Now see, if we use here the unique word, okay, along with the create index, if we use the unique word, then it is specified that the search key is the candidate. What is specified that? The search key here you are using is the candidate key. That's what purpose unique is used. But normally the simple create index, the statement of the syntax is used for the creation of the index. Now if we want to drop the index as we drop table, as we drop database, in the same way simple drop index and the name of the index, it will drop the particular index you have created. So drop index and then name of the index. For example, we have created department index. Okay. So in this way, we can create the index and we can drop the index. So most of the database system allow all type of indices.